So, hello everyone. Thank you for this great opportunity to present on the topic of standardization. I'm Ádám Wolf. I have an academic background in mechatronics and robotics. Currently, I'm finishing my industrial PhD, the topic of which is closely related to my activities at Takeda. I was part of the R&D organization, the Pharmaceutical Sciences organization based in Vienna, where I was focusing on laboratory automation and the integration of lab robots. Currently, I'm transitioning to a new role in manufacturing and supply with a broader scope, including logistics, production, but also focusing on robotics and learning from what we have developed in the R&D setting. I also have the honor to be in the board of directors of the Standardization and Laboratory Automation Consortium, or SILA in short. And during my presentation, I will briefly introduce some of the key concepts of the SILA 2 protocol. But first, let us look on the big picture. When we talk about standardization and laboratory automation, we need to consider the different layers and different aspects of what needs to be standardized. And maybe what are great examples? To mention one, starting on the hardware side, closest to the sample, to the number one asset of interest, we should mention LAPP, different types of container, and the SBS microplate, or the NCS-LAS microplate, is certainly a great example of widespread standardized format that facilitates the labware's integration and interfacing with a variety of instruments, including analytical instruments, but also supportive devices such as labware transportation robots, conveyor belts, and so on. Together, these two layers, the physical layers, are what we consider the assets, the physical assets, about which we need appropriate information models or ontologies to facilitate their integration with the overarching control layer that makes it possible to orchestrate the workflow, to define the steps of the workflow, the recipe of what needs to happen to the sample within an appropriate representation format or language that the user or any requester, another system, can use to convey the request. The purpose of experimentation in general, be it R&D or QC, is to get data out of the system about the samples. To convey this data in an appropriate format, we need standardization again. There are examples such as the Analytical Information Markup Language or the LAPP initiative. Now, we see the current state features a great level of complexity and heterogeneity, which hinders the ease of integration and makes it really complicated and costly to put together multi-layer complex systems. So what we propose and what the vision is to create an overarching, holistic and agnostic reference architecture model by outlining the layers and components in a generic way of the system architecture, to define the communication between the components by creating the appropriate semantics of the decomposition of the workflow, and also binding the levels of the decomposition to the levels of the control architecture. To do that, we introduced the LAPP framework, and this is also the subject of my industrial PhD, and connected to the activities, what we did at Takeda together with our partners, the laboratory automation plug-and-play framework. The first pillar of this concept, of this framework, is the previously mentioned semantic layer, the decomposition of the workflow by outlining the canonic layers, looking at how a procedure or experiment is decomposed into tasks. These tasks we consider device-level elemental action items that are dealt with by distinct devices or robots. You will see in the next slide how it reflects in the layers of the control architecture. Now, further down, we are talking about subtasks, and then we arrive to the low-level side that is closest to the hardware and specific to the actual type of instrument. In this example, we consider supported robotics and liquid handling. In both cases, we can talk about motion sequences broken down into primitives and actuator primitives. So on the dimension of the control architecture, we can see that in such a generalized system architecture, we have a scheduler, a laboratory execution system that effectively executes the procedure, the experiment, which it comprises tasks. And as I mentioned, these tasks are dedicated to devices. We need dedicated control units in the lab, especially in R&D. These are, in most cases, PC software coming from the vendor of the device or a middleware for the robotic subsystem. On the bottom, we have the embedded controller, a microcontroller, a programmable logic controller built into the device or into the robot's onboard system. Now, another aspect that I mentioned on my first slide is information representation about the assets. And again, the primary asset is the sample. In the closest connection to that, we are talking about containers and labware. To aid the robotization of the process, we need to define the appropriate parameters of the labware. And for robots, to mention just one aspect, this is, of course, dimensions and positions, be it the external gripping dimensions for supportive labware transfer robots or the internal valve positions for liquid handlers. One layer up about the devices, the instrumentation, we also need to represent the positions for the robot to be able to perform, for example, picking or placing for the labware transfer task. So this framework features a hierarchic position representation concept, where coordinate transformations between frames of references basically represent the positions. We have seen in the previous presentations the use of optical markers to aid the recognition of the first frame of reference for a mobile robot to deal with the device. And when this frame of reference can be connected with the internal positions of the device, and these connections are fetched from a common database, let's call it a digital twin, a virtual representation of the device itself, then we can ultimately achieve what the name suggests, also laboratory automation plug and play, without the need for manual teaching. So to arrive to the communication side of the standardized architecture, I want to say a few words about a communication protocol called LAPP, which is maintained by the consortium, the SILA consortium, which is a not-for-profit membership organization. We have different working groups, domain-specific ones, such as for robotics, and also the core specification is constantly developed and maintained. This specification has 3 layers: the core, the conceptual, technical mapping, and then the most important one, probably the feature definition, which represents the semantics, the functional service description for each active asset in the laboratory. Now, these active assets, the devices and the robots in the SILA ecosystem, are called servers. They provide a set of features that contain commands with appropriate parameters. And a feature definition is essentially the contract between the server and the client. Now, a client can be basically anything: another device, an overarching control layer, the scheduler, the orchestrator, or the limbs directly. And via the feature definition, it can interface with the servers with the devices in a plug-and-play fashion. To demonstrate the feasibility of the LAPP concept and how the SILA labware transfer feature definition can be implemented for stationary and mobile robots, we took a multi-step approach. First, together with the SILA Robotics Working Group, we assessed the required capabilities for supportive lab robots, and we identified the labware transfer capability to be the most ubiquitous one and most requested one. So we came together and created a harmonized feature definition first for stationary robots, for which we demonstrated feasibility in the form of a hackathon, and then for mobile manipulators together with an academic partner, the Hungarian Open University. The next step was to create an industrial pilot implementation. This is a project that was conducted by Takeda and a partner of ours, a system integrator called Angrotech, based on Omron components. We created a solution that featured the canonic layers of the LAPP reference architecture model and the semantics being based on a SILA-2 communication backbone. So on the right, you will see a video of the robot performing a labware transfer by first changing its end effector to accommodate an SBS microplate in this case. In the meantime, the source device, the fridge, opens its door, exposing the handover site, which is an essential part of the sequence and also defined by the labware transfer feature definition. Then the robot navigates to the destination site, uses an optical marker, also in this case, and places the labware. Now it's important to point out again that this is all controlled by a scheduler from Biosero via the SILA communication protocol and the standardized reference architecture that we have outlined. So this on the very top features a scheduler, and via the SILA server and SILA client layer, we interface with the middleware layer. So I mentioned that in the case of mobile manipulators, this is a complex subsystem in itself. We have a fleet manager, we have a control software for the robot arm, and on the bottom, the mobile manipulator itself features several subcomponents. The source device I already showed was a fridge with a door opener, also controlled via SILA, and the destination device, a liquid handler that runs sample preparation methods. Also, a prototype SILA server was developed for this one. So with that, I'm at the end of my presentation. Here is a link to my project website. Here you can see previous presentations and papers if you're interested in more detail about the aspects of the laboratory automation plug-and-play concept. Thank you very much for your attention, and I'm looking forward to your questions.